All right, section 4.5, exponential and logarithmic equations. Should go quick and smooth, I hope. So we're going to look at exponential equations, logarithmic equations, and we're going to revisit compound interest. It'll be the same formulas that we used before, but now that we have logs, we should be able to answer different kinds of questions using the same formulas. So we'll revisit some of those. Okay, exponential equations. An exponential equation is one in which the variables occur in the exponent. Some exponential equations can be solved by using the fact that exponential functions are one-to-one. So this means that a to the x equals to a to the y implies that x equals y, right? So if we know that, just to put some numbers on there, 3 to the power of x plus 2 equals to 3 to the power of y plus 3. Because they both have the same base and because they're equal to each other, this little property is letting us know that we can conclude from here that the exponents must be equal to each other. X plus 2 must be equal to y plus 3. Right? That's what this little thing is letting us know. Exponential functions with the same base. Good. So that'll be a useful tool to be able to solve a lot of exponential equations. Good. So as a general guideline, when we approach exponential equations, we want to isolate the exponential expression on one side of the equation. We want to take logarithms of each side and use the law of logarithms to bring down the exponent. I also refer to this sort of as the definition of logarithms, and then solve for the variable. Okay, so we'll kind of explore what all those things mean in this first example. So consider the equation 3 to the power of x plus 2 equals to 7. Part A, find the exact solution of the equation in terms of the logarithm. Part B, use a calculator or technology to find an approximation to the solution, round to 6 decimal places. Okay, so part A, let's find the actual answer. Part A, we have 3x plus 2 equals to 7. Well, one thing we could do is rewrite this as a power, an exponential number with base 3, and we'll leave that as a plan B. We'll come back to that. But for now, what we'd like to do is apply a log to both sides of the equal sign. Right? The reason we want to do that is because one of the really important properties of logs is that is the one where we have this one. If we have log base a of any number raised to the power of, say, I don't know, w, like this, equals to y, say something like this. One of the properties, and in fact we don't even need the equals y. One of the important properties of logs is that it lets you bring this exponent that's up here, this guy, it lets you bring it out in front. We can say that this whole thing is equal to log base a of x multiplied by the w out in front here, like a linear factor. Right? So it lets you bring that exponent out in front. Here, the unknown variable that we're trying to solve for is up in the exponent. And this property is the only thing we know of that allows us to get it out of the exponent and be able to solve for it. Right? There's nothing else we could do. We cannot divide by 3, multiply by anything. We can't add or subtract anything. There are no other operational symbols or operations that we know that would allow us to simplify this except for this. Good. Okay, so we gotta apply a log to both sides. We're allowed to do that as long as we maintain the equality of the equality. We could do whatever operation we want. So we choose to apply a log to both sides. Now you can apply any log you want as long as you're applying it to both sides. So as long as you're maintaining that equality, you can apply a log to both sides, and you can make it, any index you want. We can make both of these 8 we want to, log base 8, that's fine. Or we can make this log base 13 if we want to. Sure, pick your favorite log. However, why not make life easy, right? There's a nice easy button in our calculator for log base 10, so why not use log base 10? So log base 10 is a very popular log to use, right? Likewise, it could be any log. Another very common, very easy log to use, I'll put it over here, or, and as long as the stylus is working, let's do this. We can say ln. ln is another very popular log that could be used, right? It's log base e. Either way, let's just keep going. It's a fairly simple example. Okay, so now we get to bring the exponent out in front like a linear factor. So we're going to be able to bring this guy out in front. And same with this guy, we get to bring it out in front. Good. We'll solve both of them side by side. We have x plus 2. And then we have log base 10. And then if it's log base 10 by default there, then you just don't write anything. Just makes it easier. And then log of 7. Right? By default, if there's nothing written there, we know it's log base 10. And it's really annoying in some parts of math where they don't write anything, and by default is the exponential one. So be careful with that. When you move forward into some other field, some of the engineering fields and stuff, I'm pretty sure electrical engineering, I've seen some of their graduate work. I saw some formulas, and somebody asked me to help them figure out what they were doing there, and it stumped me for a really long time. I kept staring at this thing saying it's base 10, and it was just bugging me, and eventually it occurred to me that they meant log base e, and they just wrote it this way, and it was meant base e. So anyway, just be careful. I think some other fields take slightly different notation, right? It's one of the big hurdles of science, notation. Okay, so next what we're going to do is we're going to divide both sides by this. Let me write it down. So next we're going to divide this side by log of 3. Divide this side by log of 3. We're allowed to do that because this is a number, right? Remember, we're not allowed to divide by log. That's a mistake people make very often. They see log of 3 and they divide by log, and somehow the logs cancel, so this equals to 3, right? That's not true. But we can divide by log of 3, right? This is a decimal. It's the decimal such that 10 to the power of this number equals to 3. Good. So some decimal value is represented by this notation, and we can divide both sides by that decimal value, which would result in x plus 2 equals to log of 7 divided by log of 3. Good. Now we just subtract 2 from both sides, and we get our final answer. X equals to log of 7 over log of 3 minus 2. Any questions about that? No? Okay, so there was nothing special to log base 10. It's just an easy button on my calculator, so why not use it? But likewise, ln is popular, so we could just solve it using ln, and it's going to be the exact same process. We get to move the exponent out in front like a linear factor. Get that page number there. So this is x plus 2 ln 3 equals ln 7. Divide both sides by ln 3, so x plus 2 equals to ln 7 divided by ln 3. Oops. And so x equals to ln 7 divided by ln of 3 minus 2. Good. Again, note that log base 10 of 7 does not equal to ln of 7, and log base 10 of 3 does not equal to ln of 3. However, the ratio of these two, the division of these two, will be equivalent to the division of these two. Good. So you get the same answer either way. Any questions at all? No? We're good? No questions, no questions, no questions? So another approach to this thing would be to use graphs. Okay, I think that's what they wanted you to do for part B, right? Use a calculator to find the approximation of the solution, round to 3 decimal places. So we can use graphs to solve it, and we'll do that next. And then that also opens up another idea of how to solve this that would require some graphs to do it. But, okay, so then let's just type this into our calculator, get an answer, and then check it. It's important to always check your work with these guys. So using my easy buttons, I have log of 7 divided by, oops, clear, log of 7, close parentheses, divided by log of 3, close parentheses. That's going to give us some answer. This thing's way too big. Oh, that's too small. So log of 7 divided by log of 3 is going to give me some answer, that decimal. And that decimal is going to be the same as ln of 7, close parentheses, divided by ln of 3. ln of 3. Either way, we get the same decimal. And now that decimal gets subtracted by 2. And we get that value, negative 2288, rounded to 4 decimal places. Good. And so we check it. Going back to the original statement, let's see if that's the number, that's the value that solves it and gives you a true statement. Is it true? Check. Is it true that 3 to the power of blank plus 2 equals 7, where that blank is this negative 0.2288? So that would be minus 2. So that would be 3 to the power of 1.81. 7712, right? 2 minus 0.2288. 2 minus 0.2288. 7712. Yep. 7712 equals 7. Potentially, hopefully. And then we check that in our calculator. So 3 to the power of 1.7712. And yeah, it's pretty close. Works. Any questions? No? 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 Okay, now using technology to solve it. We have, this is a very useful trick. Now, there's very few things that you're actually going to use in any of your classes moving forward, right? That's not what we do here. I'm not really teaching you anything useful or valuable, sorry, or for the most part, but there are some little tricks that you actually use a lot, and this might be one of them. And we use it a lot in math as well, in this class and in calculus. And I think in a lot of the engineering classes you take, this kind of trick might be useful. Unless you're allowed to use computers to solve things, and then this trick is just kind of silly. But if you get to use a calculator and you have to solve an equation, then this is a useful trick. So solve this. Well, we found one way to solve it, logs and bring the exponent and do all that stuff, okay? The other thing you could do with your calculator is to rewrite this as one function. Here's one function, we're going to call that y sub 1 in our calculator. And then the other side is the other function, and in this case the other function is just 7, right? So we're going to have y sub 1 equals to 3 to the power of x plus 2 on your calculator, right? This is a function. And then for y sub 2, we're going to have just 7. Good. So this is the function f of x equals to 3x plus 2. So this is an exponential equation base 3. When I graph this, we'll use our calculator, but just in general, without any actual numbers, just to kind of conceptually see what's going to happen. This equation is just going to have some sort of thing like that, maybe. Okay? And then this equation over here is this one. It's just the line y equals to 7. It's just going to be something like that, right? And we want to know, when do these two things equal each other, right? So here is 3 to the power of x plus 2. That's this equation here. And we want to know this. When do they intersect? At the place they intersect will be our solution x, the one we're looking for, the place where this works. Good? Questions, 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 questions? Okay, so let's do it with our calculator. There we go. Here. So we want to go to y equals, clear old things. So we'll have 3 to the power of parentheses x plus 2, close parentheses. Let's just graph that guy for now. Let's go to window, and from 0 to 20, let's go from -5 to +5 and see how that goes. And outputs, I don't know, let's go from -20 to positive, I don't know, 100. We can always come back and change this to see if it see how it affects things. So there's my exponential function. Good. And now if we graph the y equals to 7, there's that line. Okay, well, it's kind of hard to see way down there. So now I can go back to my window and just kind of focus on this guy. Now I can see that it's just really close to down here. So let me go to my window, and instead of -5, let's go from -2 to +2. Just kind of narrowing in on the input side, and the output side, I don't know, let's go from -2 to +10 maybe, and see if that does a good job of narrowing in on it. There we go. Okay, so I found out where that intersection was. And remember that where they cross is my answer. The input, the x-coordinate of the intersect point is going to be my solution. Good. Okay, so let's see. So then now if I go right here where it says calculate, right above the trace button, calculate, second, calculate, and then I want to go down to intersect. Intersect, hit enter. And now it's asking you for the curvatures. So there's only 2 equations on there, so this should be easy. Just hit enter once, hit enter twice, since there are only 2 of them. If there was more than one equation on there, like let's go back over here. Let's throw in another random equation onto here. I don't know, x equals y equals x, for example. Just another random graph on there. There it is. So now when I go to the calculate intersection, you know, it's a dumb calculator from the 80s, 80s technology here. So if you go up and down, it'll let you scroll through the 3 different equations I have. So that when you want to find the intersection, it wants to know which 2 equations would you like to check if they intersect or where they intersect. So you can just hit enter to select it, and then you can toggle between the others so you can get to the one you want. So right now it's blinking on that one, and that's what the one I want. Hit enter. And then it says guess. So you can go left and right and travel across one of these functions until you get to a pretty good guess. Now again, there's only one place that these two cross, so it's kind of a silly question. But if it was a more complicated curvature, you know, like a cosine up and down, and another line through it, there might be lots of places where the graphs intersect. So then, in that case, it would be a little bit more appropriate to ask you which intersection you're talking about. But anyway, so we guess, we get pretty close to it, enter, and there's our solution. The x-coordinate of the intersection is going to be our solution. Good. So that's how we can use our calculator to solve it. Well, we can do a similar thing with other technologies that graph, like Desmos. Graph both equations, figure out where they intersect. So this is generally a pretty useful tool whenever you're trying to solve any kind of equation that's really complicated. There might be a really ugly thing on the left side. There might be a really ugly equation on the right-hand side. As long as they're functions, as long as both sides are functions, then we can write a function on the left-hand side, a function on the right-hand side, graph them, see where they intersect, and all the intersection points are solutions to the original equation. Any questions? Oh, my sketch was way off then because they cross over here, right? But this was just sort of in general. Questions, 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 questions? No? None? None, none, none? Okay, let's see what the author did. Very similar, applied log to both sides. And then divided, yep, same thing I did. Yep. Check it, okay. Oh, they didn't, using a calculator we find the decimal approximation to be equal to this. Oh, for part B they meant use a calculator to convert this into a decimal. That's what they meant by use a calculator to find an approximation to the solution rounded to 6 decimal places. Okay, I interpreted this wrong. They just meant to convert your exact solution into a decimal approximation. I thought they meant starting from scratch, starting from up here, use technology to solve it, which is what we did. Oh well, we went over a very useful calculator trick to help you. I wouldn't say it's a trick, it's just a useful way of solving equations using a graphing calculator. Good. Questions, questions, questions? No, 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 no. Whoops, why is it giving us the answer? Okay, okay, this is broken. It just wants you to solve this, and I don't want to sneak down here and show you the answer, so I'll just write it over here. It is... Actually, let's see if this thing will work today. That thing. Lost it. There it goes. Okay. So, solve e to the 2x minus e to the x minus 6 equals to 0. Okay, so it's an exponential equation because the unknown variable that we want to solve is up in the exponent. It's not quite as easy as before where we just applied a log to both sides and we're able to bring the exponent down. Remember that that property only works as long as we have something that fits this form, log base a of x to the w. If we have one exponential number like this inside the argument of a log, that's when we can bring it out and say that it's equal to w times log base a of x, right? No variations on this. Don't make up your own way of this working. There's nothing in our properties of logs that says that if we have, you know, this x to the second plus x to the y plus 9, that you can do anything that involves just bringing these exponents out, right? And also we don't have a way of separating this into the addition log base a of x squared plus log base a of x to the y, right? We don't have that. We can separate it if there's multiplication in here. We can separate it into the addition of, the addition of logs if the arguments in here would be multiplied. And we can also rewrite it as a subtraction, as a difference of logs, if the argument inside here was a big fraction. We can do that. But if we have addition or subtraction inside the argument of a log, we're out of luck, right? Those properties do not work. And also, we're not allowed to bring this 2 out in front, or this y, or rewrite this as a 3 squared and bring out the 2. Right? We can't do any of those things. So none of that is helpful right now. So what we have to do is realize that this one is a quadratic in disguise. Right? This is e to the x squared minus e to the x minus 6 equals 0, right? So now we can do a simple u substitution. Let u equal to e to the x. Okay. So then, in fact, you know what? I'll give it to you in color. About blue. Let u equal e to the x. So we're going to have a u here, and then another u. And this is squared minus u minus 6 equals 0. Okay. So now it looks like a quadratic, right? And it should be a straightforward quadratic. It should fit this form. Two numbers that multiply to -6 but add to -3. I'm sorry, add to -1. So that should be -3 plus 2. U minus 3, u plus 2. They multiply to -6, but they add to -1. Right? And then now that we've realized how to factor it, now we can come back and replace the u again with an e to the x power. E to the x minus 3, e to the x plus 2 equals 0. Good? Because we have a product equals 0, we have a multiplication here of two things, two binomials in this case, that multiply to 0, we can use the zero product principle to separate this into two pieces. Either this part must be 0, or this part must be 0. Good. Add 3 to both sides. We get e to the x equals to 3. Let me make more room here. E to the x equals to 3. Okay, so now we can apply a log to both sides. We can apply any log, but in particular, why not apply ln? Ln e to the x equals ln of 3. Good. And then one of the properties of logs is that these two are inverse operations. Ln of e to the x, these two operations undo each other, and this just becomes x. So we get that x equals ln of 3 as one of our solutions. Good. Over here, we do the same thing. We subtract 2 from both sides of the equal sign. Minus 2, minus 2. And so we get, e to the x equals to -2. And that should be where we realize that that is leading to a dead end. Right? Remember that the graph of any exponential function where the base is bigger than 1 is going to have this sort of a shape like this. Right? This is a to the x power where a is strictly greater than 1. Good, 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 good. And if a was a value between 0 and 1, it would have this sort of shape that comes this way. Oops. It would have this sort of a shape that comes this way like that if a was trapped between 0 and 1. Either way, the outputs are never, ever, ever going to be negatives, right? So the output, the answer to an exponential number like this is never negative. So this is no solution. So the only answer we have is x equals ln of 3. Now we can leave it like that as an exact answer. Again, we can use our calculator to turn it into a decimal approximation. And if we turn it into a decimal approximation, then it becomes easy to again use our calculator to check and verify that in fact this is the right answer. So you just type that in your calculator, ln 3. I'm getting x equals to, oops, which color now? I'm getting that x equals to 1.09861. Let's just leave it at that. Good. So now let's check it. Is it true that e to the power of twice something minus e to the something minus 6 equals 0, right? Where that something is this decimal, 1.09861, 1.09861. So it's just a matter of typing into our calculator and confirming that it does give you a true statement. Good. Let's check it. I'm going to check it real quick here on mine. Check it on yours. Oops. 2 times 1.09861 e to the power of that plus, minus e to the power of 1.09861. Yeah, I'm getting pretty close to 0. Any questions? True. No? Good, 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 good. Okay, let's see what the author did. Same thing. This is a quadratic in disguise, so we can rewrite it this way. They didn't bother with a u substitution, but I did. I wrote this u substitution. And then that gives you this, which gives you that. No solution for this side, and there's only one solution for that guy. And then he didn't do the check, but you know, plug it in, you check, and you see it works. Good. Any questions? Okay, logarithmic equations. Logarithmic equations are going to be similar. We have equations we're trying to solve, and we get to use logarithms as a way of solving them. And we want to be able to apply this statement here, that if an equation has, say, log base 7 of something, happy base, is equal to log base 7 of something, sad face. Well, whatever these are, they must be equal to each other, right? They both have log base, the same index, right? So this property is saying that they must both have the exact same argument. That must mean that this is equal to this. Sad face. Oh, this is a mustache. Well, whatever. Any questions? Sort of, kind of, maybe, sort of, kind of. Okay. So, guidelines for solving logarithmic equations. Isolate the logarithmic term on one side of the equation. You might first need to combine logarithmic terms, so we get to use our properties to contract or expand logs. So in this case, we'd like to contract them into one big happy log. And then we might use the definition of logs. We might get to apply this property where we apply log to both sides of the equal sign. So they vary a little bit, but we've got a variety of tools to help us. So here's a couple of examples. And for both of these, I refer to it as the definition of logs. Remember that if we have log base a of x equals y, then by definition there's this little thing, this to that power must be equal to that, right? If and only if and only if it's true that a to the y power equals to x. If you forget that whole thing, just think of a simple example. So 2 to the power of 3 equals to 8. So that must mean that if we kind of go backwards, log base 2 of 8 equals 3. Right? Again, this little circle, 2 to the power of this guy must be that guy. Okay, so this might be a little, might be helpful in remembering the property. Okay, so that's what we want to apply here. Remember, ln is log base e, so there's a little e there. E to the power of that guy must be this guy. And that's it. That's all you have to do for this one. E to the power of 8 is equal to x. This is just some number. I can just use my calculator to find it. Good. This is just e times e times e times e multiplied by itself 8 times. Questions? 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 No? No? Okay. So we can use our calculator. Okay. Let me launch it and see how it does. I try not to keep the program open because it slows down the stylus I've found. I have too many programs open. So let's quit from here. And so e to the power of, second, e to the power of 8 equals this number. 29, 80, 95, 80. 29, 80, 95, 8, approximately. Good. And we can check it to make sure. Check to make sure. Well, if it works, it must be the value such that ln of that number is approximately equal to 8. Right? So we can check it by plugging in that number right into here, going back to the original equation. And again, we can use our calculator to check that. 958. Okay, so if it's true, it must mean that ln of 2980.958 approximately should be pretty close to 8. And it is. A little bit of rounding issues. Any questions? No? We're good? Okay, this next one, same thing. We want to use this property that this little base to that power equals to this, right? It's the definition of log. You know, a lot of people stare when they look at these. I feel like they just get stuck with this word. Their eyeballs just hit this right here, and they don't know what to do with it. They're trying to remember what is the definition. Logs, you know, they try and solve for L or something, like they're variables or something. Right, so you really got to get away, you know, get past that and focus your attention. Your eyeballs should be focused on this little index right in there. Right, we know that this raised to that power must be equal to this. That's how we want to solve for whatever is inside the argument of the log. In this case, where we have 1 log equals something on the other side, particularly if that other something doesn't have any logs in it. Good. Okay, so applying that property, very simple. We get that this must mean that 2 to the power of 3 must be equal to 25 minus x. Good. All right, well, 2 to the power of 3 is just 8. 8 must be equal to 25 minus x. And now we just solve for this guy. Minus 25 minus 25 gets you to 17, so minus 17 minus x, and then divide both sides by that minus, so we get that x equals to positive 17. Good. Check. log base 2 of 25 minus x. Oops. Something. Equals to 3. So we're going to check to make sure that 17 is the number that goes in there. And we'll use our calculator to do that. Okay, so that must mean that log base 2 of 8 must be 3. And, well, this is one of the obvious ones we already know. Log base 2 of 8 must be equal to 3. We did that over here, actually. Log base 2 of 8 equals to 3. Good. Definitely true. Okay, so they were just kind of conveniently easy numbers, but what if they were really ugly numbers that we didn't really know just by looking at them? Let's use our calculator to check it. So again, we're not solving it, we're just checking to make sure that this really does equal 3. Okay, so let's do that with our calculator. We got a couple of choices. For one thing, well, before I go there, remember we have this change of base formula, right? If we don't know that this equals to 3, it's just not off the top of our head, we don't know that that's true, and we want to find out what is this, remember that our change of base formula from yesterday says that we can convert it into any index we want, log base anything we want, by using the change of base formula, and so we can change it into something more convenient like an ln function, ln of 8. I don't know what log base 2 of 8 is, so I can use ln of 8 and divide it by ln of the base that you didn't want to use, the index you didn't want to work with. So this division, this ratio, will be equivalent to this, right? And since we know the answer is 3, I'm saying that this will be the decimal such that e to the power of that decimal equals 8. This will be the decimal such that 3 to the power of this decimal equals to 2. But then when we divide them, I know that they're going to be equal to 3. Good? Let's check all that. Calculator. Okay, so ln of 8 equals that decimal, right? That's the decimal such that e to the power of that decimal, 2.07944, something like that. That's the number such that e to the power of that decimal equals to 8. That's its definition, right? Given some rounding issues, pretty close to it. Good. And then ln of 2 gets you to that decimal. So ln of 2, that notation represents the decimal such that e to the power of that decimal, 0.693147, that whole thing, it's approximately equal to 2, right? Okay, so now the numerator is 2.07944, this number, divided by 0.693, this decimal right here. The division of those two is going to be pretty close to 3. Right, so 2.079441542 divided by 0.69314718006. Pretty close to 3. Okay, well, we could have just saved ourselves a lot of the trouble here. I was just trying to point out what these decimals really represent, but really we just type it all in one sweep. Ln of 8 divided by ln of 2, and we see we get an answer of 3. Good. Okay, again, as long as we're just checking what things are, there is a way for some of you to be able to figure out what log base 2 of 8 is directly. This won't be in every calculator, just some of the newer ones have the software for it. So the way you would do it is to go over here where it says math, this button that says math, and then you got to find the one that says log. And I don't know where it is exactly. There, log base. It says log base, like this. Again, so hit math, and then right here you get this menu, and under math you scroll down until you see log base. Like I said, most of you probably won't have this. Only some of the newer calculators have them. If you don't have it, then you're stuck doing it the old way, one of these other ways. Okay, but if you do have this, then you can hit enter, and see now it gives you a way for you to type in the little index of the log. So I can type in a 2 there. Go over, and then I can type in an 8 here, and then go over, and then hit enter. There. Good. You know, TI is in a very difficult spot because you know, something like this is actually really controversial in math. A big chunk of math teachers love this feature. They're happy that the calculator now has this feature, and there's a whole bunch of other math teachers that are very upset that the calculator put this feature on there and is now making it easier for people to solve things. So the company is kind of between a rock and a hard place. It can't please anybody. No matter what they do, a good chunk of people are going to be mad at them. And at the same time, you got, you know, iPads and phones and computers that are becoming more and more affordable and ubiquitous everywhere, and so it's becoming difficult to be a standalone calculator company. But we'll see where they go. Anyway, questions? No? No? We're good? Good. Okay, solution A, solution B. Okay, so here's a loose application of this stuff. So logarithmic equations are used in determining the amount of light that reaches various depths in a lake. This information helps biologists to determine the type of life a lake can support. So as light passes through water or transparent material such as glass or plastic, or gases, right, an atmosphere, some of the light is absorbed. It's easy to see that the murkier the water, the more light is absorbed. The exact relationship between light observation and the distance light travels in a material is described in the next example. Okay, whoa, let's zoom in a little bit. So if I sub naught and I denote the intensity of light before and after going through a material, and x is the distance in feet that the light travels in the material, then according to Burr-Lambert law, we have this relationship is true, where k is a constant depending on the type of material. Okay, so 1 over k, negative 1 over k, ln of I over I naught equals to x. So I naught is the initial intensity, right, before it hits a surface, let's say the surface of the water, the intensity of light at the surface of water, and then it goes through a certain depth. Depth is x, so maybe 3 feet underwater, 10 feet underwater, 100 feet underwater, so the depth underneath. Capital I is the intensity of the light at that point, at that depth. And then K is some constant related to the particular substance we're talking about, whether it's glass, whether it's water, and even within water, there will be different constants for different types of, waters. Water, whether it's ocean water, whether it's freshwater lake, just how much sand is in there, how much pollutants are in there, stuff like that. So this sort of thing is also very useful if you're looking at like oil spills, and now it's not just affecting, there's a whole lot of things it's affecting, and one of those is the transparency of light. If the water is very polluted with all that oil, it's going to make it more difficult for light to make it all the way down to the depths it used to make it to. And then that will affect those organisms deep down there that are counting on that little bit of light that was getting down there. So anyway, so this is the property that applies. There was no explanation given as to where this comes from. So at this point, we're just expected to understand the formula, not really worry about where it comes from, and then apply it, use it, love it, and move on with our lives, right? So here's the formula. So here's an example. So for part A, it says solve for I. Solve for capital I. So we have that -1 over k ln of I over I naught equals x. So solving for capital I should be pretty easy. Ln of capital I over capital I naught is equal to kx, right? Multiply both sides by -k. And now we want to use the definition of logs. Remember, this is a little e there. E as the index raised to that power must be equal to whatever's in there. So I can conclude that, let's get rid of that page, I can conclude that capital I divided by I naught is equal to e to the power of -kx. Good. And now if I multiply both sides by I naught, I've solved for capital I. Capital I equals to I naught times e to the -kx. Good. So that's the answer to part A. Solve for capital I. Okay, now for part B, for a certain lake, K equals to 0.025, and the light intensity is 14 luminance, I sub naught. So the initial intensity when it initially at the surface of the lake is 14 luminance. Find the light intensity at a depth of 20 feet, so x equal to 20 feet. Make sure that the units match, and then up here, this thing was given in feet. The distance was given in feet, so that works fine. And then the light intensity was not was given in luminance. I think it's implied that light intensity is measured in lumens. Sorry. Good. Okay, so for part B, they tell us that I sub naught is equal to 14, and that x is equal to 20. So we have that guy, we have that guy. Oh, sorry, and that k was equal to 0.025. So then it just becomes a plug and chug kind of question. So one thing I'm pretty disappointed with this book about is the word problems are kind of easy. They lack imagination, and they focus a little too much on formulas that are unexplained. But do what we do. All right. Okay, so there's the thing we need to solve. We can just punch that into our calculator and get a decimal approximation. So e to the power of -0.025 times 20 equals that, and we multiply that by 14, and I'm getting approximately 8.5 lumens. Oops. 8.5 approximately. Good. So at a depth of 20 feet, so light was 14 lumens in the surface, 20 feet underneath the water, the light intensity is now only 8.5 lumens. Questions? Approximately 8.5. Light intensity at a depth of 20 feet is about 8.5 lumens. Any questions? No? No? Okay, compound interest. We've already explored these formulas. Remember that if we have simple interest, an interest rate, say a 1-year interest rate, and we want to find out what the balance is at the end of 1 year if it's compounded only once, then this is the formula. Now, it doesn't have to be a year. It's just that that's the most common way of doing this, because by default, interest rates in our society, at least, are always given in terms of a year. Whenever you get a credit card, whenever you get a any kind of loan, whenever you buy a house, every interest rate is given in terms of an annual rate. It's just a way of standardizing it. Nothing special about that. The government could have just as easily mandated that all interest rates be given on a daily basis, your daily rate, and I think that would have been easier, I think. It would have been easier in concept. The problem is that the actual number you work with would have been really, really small. So you'd have a lot of zeros in there. Very easily made it every month. The interest rate is given on a monthly basis. It's just a standardization, just to make it easier for people to maneuver through our financial infrastructure. But there's nothing really special about it. Okay, but by default it's 1 year. So if we have interest rate given in terms of an annual rate for 1 year, then this is the formula for simple interest earned after 1 year. If, on the other hand, it's compounded n number of times per year, like maybe compounded monthly, compounded daily, the compounding, remember, it's the time when they do the formula, when they actually check how much interest is earned, and then they deposit the interest earned into your account, so that the next time it gets compounded, they give you interest on the interest earned the first time, right? So it's kind of like a maintenance thing. How often do they look into your account and do maintenance on it to add the interest you had earned, and thereby letting your account be a little bit bigger the next time they do maintenance on it, so that they can, again, have your interest earn interest, right? The secret to being super wealthy is just having a bunch of money, and then your money makes money, and then that money makes more money, and you just got to kick back and, have margaritas by the pool. Let your millions make more millions, and people think you're brilliant because you're so rich, you make so much money, right? Just got to have, a really rich daddy that gives you a couple $100 million. There you go, rich. You're smart, great businessman. At any rate, off that rant. And then we looked at compound interest. We got this formula for compound interest, right? And this means that it's compounded continuously, right? When we have a situation where the interest is compounded, not just every second, but every fraction of every second. Continuously compounded interest, we'd have this sort of formula. In our financial system, we work with compounded annually very often. We work with compounded monthly very often. Credit cards like to compound monthly. That's when they do the maintenance, right? They check once a month. How much do you owe? Okay, let's charge you a fee for what you owe this month. And then if you don't pay any of it, the next month, when they do maintenance on it again, well, now they charge you money on the money they charged you the previous month, right? Now the debt is earning more debt. Debt earns debt. Debt earns debt. So if you just ignore it, that could really blow up, right? That's the secret for them making a bunch of money and for people staying in debt. The fact that it gets compounded, right? Your debt generates more debt. Okay, so credit cards work very often on monthly compounding. The stock market likes to work very often on daily compounding. Every single night, large institutions borrow money overnight. They call those the pink sheets. So if anybody out there is interested in becoming a broker in Wall Street, and that's a really big market. That's people lend institutions billions and billions of dollars for 1 day, just overnight. The market closes today at 3 in the afternoon, and on computer at least in their system, sometimes they would like to have a bunch of cash available to them, so they borrow it for one day, and then in that one day they pay interest on that, so they pay a daily interest rate. Good. There's a really famous case you can look up. There's a bit of a rant, but there's a really famous case of a guy that worked for Bank of America, and I believe it was China that had borrowed a bunch of money from Bank of America, like billions of dollars. You can Google it and find the details. I'm really rough with details, but anyway, China borrowed a bunch of money from Bank of America, and then China was paying it back to Bank of America. And this guy was, high up in the ranks of a Bank of America, and he was involved in that whole computer transaction. So anyway, he arranged it so that China paid them back on February 28th, and then it appeared the next day on the Bank of America computer system that China had paid them back on March 1st, February 28th, March 1st, looks good. Except that this happened to be a leap year, right? On leap years, we have one extra day, February 29th, which also happened to land during a business day that he could work with. So when China paid back the money, he fudged it, so he stole the money for one day and put it into the market so that he could lend it out for the one day and earned a bunch of interest. I don't know how much. Probably hundreds of millions of dollars in interest, since it was billions of dollars that he stole for a day. He went over to the markets, to the pink sheets. This is all electronic. He went over the pink sheets. He borrowed, he lent out all that money. He made a bunch of money in interest. And then the very next day, he put the money back that China borrowed back into the Bank of America computer systems. So he only borrowed the billions of dollars for one day and made hundreds of millions of dollars for the one day in the pink sheets. So daily interest rates, they're a thing. Would have been a great heist, except since everybody knows about it, he probably got caught then, right? Luckily, it's white-collar crime, so he probably didn't do much time or anything. They probably just gave him community service or something. Steal 20 bucks from a liquor store, you can get, years in prison. Steal billions of dollars for one day, and a little community service. Maybe a light sentence. Anyway, man, I go on rants today. Let's look at some examples. A sum of $5,000 invested at an interest rate of 5% per year. Find the time required for the money to double if the interest rate is compounded in the following methods. Okay, so we know our formula for compounding. For this one, semi-annually, it's going to happen twice a year. So that means n equals to 2. Semi-annually is just going to be this formula. We'll replace n by 2. We know the interest rate. We know the principal. And we know that it's going to double. Okay, so let's look at our formula for this one. Go away. So the formula for this one was going to be that the balance of my account is going to be the principal 1 plus r divided by n to the power of nt. And for semi-annually, that means that n equals to 2. And we know that p equals to 5,000. And we know that r equals to 0.05. And we're looking for t, find t, find the time it takes for the principal to double. So I know that the output of this thing should be twice the original principal amount, twice p, right? So it should be equal to 10,000. Good, 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 good. Okay. So we can replace these values in here and get this statement. We're looking for the value of t such that 10,000 is the output when 5,000 is invested, and we have 1 plus 0.05 divided by 2 to the power of 2t. Good, so now it's just one little letter that needs to be solved. Let's simplify life. Let's divide both sides by 5,000. Divide this side by 5,000. And so we see that this is just going to be 2. 2 equals this thing. 1 plus 0.05, well, let's just change it to this is just going to be 2.5%. 5 divided by 2 is 2.5%. And then you add that to 1, so it's just going to be equal to 0 to 5. 2.5%. Raise the power of 2t. And now, the thing we're trying to solve is in the exponent, so that means we have to apply our log functions to solve this. So I'm going to use log base 10. Log base 10 of 2 equals to log base 10 of 1.025 to the power of 2t. Right, so now that means that this exponent gets to be brought down like a linear factor, and I'll end up with 2t times log of 1.025 and then log of 2. Divide both sides by this log and 2, and we solve for t. So divide by 2, log base 10 of 1.025. Divide this side by 2 and log base 10 of 1.025. And then we solve for t. So t is going to be equal to log base 2 divided by 2 times log base 1.025. Good. Okay, so now we get our calculator and check that. I would start with these two, and I guess I can also separate it as being times 1/2 the product of that division. Anyway, different ways for you to type it in. So log of 2 divided by, and then in parentheses I'm going to put 2 times log of 1.025. Close parentheses, and 14.03551. 03552. Good. Questions, 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 questions? You can check. Is this true? Is this how long it's going to take for it to double? Okay, remember it was 5,000 times 1 plus 0.05 divided by 2 to the power of 2 times t. Right? We're going to check. And if this works out, if it's true, then it must mean that this whole thing equals to 10,000. Oops. That this whole thing equals 10,000. Right? It's the time it takes for your initial investment to double. Okay, so we can just type that into our calculator and check it. So 2 times 14.03552. So that's that product. And I want to say 1.025 to the power of that previous answer. I'll use this previous answer. To the power of 28.0704 times 5,000 gets me 10,000. Right? Pretty close to the answer I was expecting. Any questions? No? No? How do we turn this into a more appropriate way of saying, a more, we don't like to say decimal number of years, or it doesn't seem as palatable. So think of this as a percentage of the following year. It's 14 years, and then it's 3.55% of the following year, which we can turn into number of days. So if you take the zero, if you take the 0. If we take the 0.03552 and multiply it by 365 days, there we go. 0.03552 times 365, I get approximately 12.96. We'll just round it to the nearest whole day. That's 13. So 14.03552 years is the same thing as 14 years and 13 days. I think sounds a little better than just saying 14.03552 years. Good? Questions? No. Okay, so this was for it being compounded semi-annually, right? Just every 6 months, they're going to do maintenance on your account, figure out how much interest you've earned, deposit it onto your account, so that the following time that they do maintenance on your account, 6 months after that, now your interest you earned the first cycle also earns interest. You're going to earn a little more. So the speed at which you grow your investment is going to go a little bit faster when you compound it more often. And so when you get to the point where you get to compound it continuously, then we use this other formula, right? So compounded continuously would be this formula. Okay, so P equals to e to the RT. Oh, sorry, not P equals to the RT. Okay. A of t equals to P times e to the RT. I don't know where I got P equals. Anyway, and so we have all the values we need here. We know R, we know P. We're looking for T. And we know that it doubles, right? So here, this will turn into 10,000. The investment doubles. And P is still 5,000. E is a constant to the power of 0.05 times T. Divide both sides by 5,000. We get 2. Divide by 5,000. Divide by 5,000. These guys cancel. We get 2. 2 equals to e to the 0.05 t. Apply ln to both sides, and we end up with ln of 2 equals ln of e to the 0.05 t These two operations are inverse operations. They undo each other. So on the right-hand side, this just drops to become 0.05t. ln of 2 equals that. And so if we divide both sides by this decimal, we get divide this side by 0.05, divide this side by 0.05. These cancel, and we're left with t is equal to the division of these two values, ln of 2, 0.05. Good. So again, we can just use our calculator to find a decimal approximation. Clear. So we want ln of 2 divided by 0.05. So I'm getting 13, oops, 13.86 something. 8629. Pretty good. Good enough. Oops. $13.8629. Good. And again, we can check it by going back to our description. Is it true that 5,000, right, check. Why is it check with two C's? Check. Check that 5,000 initial investment times e to the 0.05 times this number, that this whole thing really will be equal to 10,000. I'm pretty sure it will. Any questions? No? No? So compounded continuously, the account will grow to will double in 13.8629 years. So that doesn't seem quite so easy to understand. Again, you can think of this as 86.29% of the following year, but people like to see things in terms of months and days. So let's do the same thing as we did before. So I'm going to multiply 0.8629 times 12, because there's 12 months. Right? And when we do that, you get 0.8629 times 12. Right, this equals 10.3548 months. Right, so 0.8629 years. 0.8629 years is equal to 10.3548 months. And now this is the percentage of the following month, which has 30 days. So 0.3548 months, right? This is in units of months, times approximately 30, and I know every month is a little bit different. It adds to the complexities of our silly calendar. I don't know if you ever thought about why we have such a silly calendar, but we do. This one is 10.644. Right, so now this is days. Okay, so we can just round this to approximately, say, 11 days. Approximately 11 days. So all of this was to say that your account will double in, you can either say it'll double in 13.8629 years, Or you could say that it's equal to, or you could say that it will double in 13 years, 10 months, and 11 days. 10 months and 11 days. That sounds a little bit better than 13.8629 years, right? 13 years, 10 months, 11 days. Questions, 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 questions? Okay, let's double check what the author did. Same thing I did, I think. Yep, we placed it all into here, equals to 10,000. Simplified this, logs to both sides. They also used log base 10. You could have also used log base E. And 14.04. So the money will double in 14.04 years. And over here, yeah, same deal. Okay. All right, let's take a little break, and we'll come back with 4.6. So we'll do some modeling with exponential and logarithmic equations, modeling with exponential functions. So our objectives is to look at exponential growth, doubling time, which is a popular way of looking at exponential equations. Exponential growth with relative growth rates, radioactive decay, and I didn't assign any questions involving Newton's law of cooling, so we probably won't cover it. It's interesting. It's a little too dependent on a formula that we don't actually derive. So I'm not a huge fan of it, but it just kind of turns into plug and chug kind of questions. But there's a couple of interesting types of questions there if you want to look at them. So modeling with exponential functions. So many processes that occur in nature, such as population growth, radioactive decay, heating, diffusion, and numerous others, can be modeled by using exponential functions, right? So part of what we do in math is try and explain the universe around us. And exponential growth is often something that can help us do that. Okay, doubling time. Suppose that we start with a single bacterium which divides every hour. After 1 hour, we have 2 bacteria. After 2 hours, we have 4 bacteria. After 3 hours, we have 8 bacteria, and so on and so on and so forth. Right, so here's a nice little petri dish picture for you. So at time 0, when we begin, there's only one little dot of bacteria. 1 hour later, it doubles, and then it doubles again, and then it doubles again. So that this is modeled by the function 2 to the t power. Good. Okay, so we're going to be looking at something that fits this sort of pattern where it's doubling. Every unit hour it doubles. So if we start off with 10 bacteria instead of just 1, then the initial value would be multiplied by 10. And instead of doubling every hour, it doubles every 3 hours, for example. Still looking at doubling time. That's why we still have a giant 2 here. We get twice as many every 3 hours. Then this is the little formula, how you would tweak the little formula in order to get it to double every 3 hours. Okay, so they didn't really do much in terms of, the author doesn't really do too much in terms of getting you to sort of derive this little formula. But we get to use it, apply it, and move on with this chapter. Okay, so exponential growth doubling time fits this form. N of t equals to n sub naught times 2 to the t over a power, where n sub naught is the initial amount that you begin with, of whatever it is. It could be population of bacteria, it could be anything that grows exponentially that can be modeled like this. So make sure you pay attention to the units. And then t is in terms of time, and it could be either minutes, hours, days, years, any time, any unit of time. And then a is how long it takes for it to double, right? A is the doubling time. Good. So let's use that formula and apply it here. Under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria. Right, so like on a table, we have time in t given in hours. In hours, find the model population t hours. So at time 0, we start out with 1,000 bacteria in the colony. And we know that it doubles every 3 hours. Bacteria doubles every 3 hours. So over here, hour number 3, we should have 2,000 bacteria. And then again, it doubles every 3 hours. So hour 6, we should have 4,000 bacteria. And then hour 9, we should have 8,000 bacteria. Right? That's what it means for it to double every 3 hours, starting with 1,000 of them. Good. Okay, so now that we have a good sense of what some of the outputs in this table should be, we can apply this little formula. Okay, so n of t, right, so part A, we use the formula with the use n of t. The formula is n of t equals to n naught 2 to the power of t divided by a, to the power of t divided by a. And it's kind of a straightforward plug and chug situation here, where n naught is equal to the 1,000, that's the initial starting value, and a is equal to the doubling time, how long it takes for it to double. So we said it doubled every 3 hours. And t is given in terms of hours, so the units match. T in hours. So pay attention to that. Some of these word problems trick you like that because the doubling time might be it doubles every 3 days, and then the time they give it to you in terms of weeks. How many weeks until we something? So just one little extra twist we have to be careful with. So then this formula becomes really easy. It's just going to be 1,000 times 2 to the power of t divided by 3. Good. So that's the formula that we can kind of replace in this table over here and say n of t equals to 1,000 times 2 to the power of t divided by 3. Notice what happens when t goes into each of these. It turns out that it made sense. 1,000 was the result of 1,000 times 2 to the power of blank over 3. Oops. Okay. And that blank was a 0. 0 divided by 3 is 0, and 2 to the 0 power is 1. So at t equals to 0, this whole term just becomes a giant 1, which is how we get 1,000. Okay, it matches that. So right now I'm just checking that this formula matches our intuitive idea of what the output should be for some easy whole number values. Okay, so 2,000. Okay, so this should be equivalent to 1,000 times 2 to the power of something divided by 3, and that something should be this 3. Oh, okay, so 3 over 3 is 1, right? This whole thing is just going to become a giant 1. So 2 to the 1 power is just 2. 2 times 1,000 is 2,000, right? So it doubles. You multiply it by 2 when t equals to 3. Good. This one, again, just checking to make sure that this formula gives me what my intuitive understanding of the question gave me as a result. We get 1,000 times 2 to the power of blank over 3, where that blank, that t value is a 6. So this turns into a 2. 6 divided by 3 is a 2. So we end up with 2 to the power of 2. That's 4. 4 times 1,000 is 4,000. Good. Okay, so I think maybe we start to see why the formula has this t over a here, because that tells you how many powers of 2 you should have based on the t values, right? And that's why you divide by that. So it doubles every 3 days, and if you put a 3 there, then t equals to 3 gives you 1 copy of 2, t equals to 6 gives you 2 copies of 2, and t equals to 9 gives you 3 copies of 2. Right, so when this guy is a 9, these two turn into a 3. 9 over 2 is 3. And I'll just put down here. So 1,000 times 2 to the 3rd power is equal to 8 times 1,000. It gives you that. Okay, so we're just confirming that it works. Any questions so far? So far, this seems to be matching up with our intuitive idea of what it means for this bacteria to double every 3 hours. Good, good, good. Okay, so we found the answer to part A. We found the equation, we checked it, it all works out, we're happy with it. Here is our equation for part A. But now here I was just trying some nice, easy whole numbers that gave us some very easy outputs. But we can use that formula to find any value. So it doesn't have to be just these nice, convenient values of t. It could be any other value. And we're also going to be able to use it to find things in reverse. But okay, so for part B, it says, how many bacteria are in the colony after 15 hours? When t equals to 15 hours, we have this function, n of 15. No, actually, I'll just put it in there in a second. N of blank equals to 1,000 times 2 to the blank over 3. And we're looking for 15 there and 15 there. Oh, okay, it's still going to be a pretty easy one, right? Because it turns into a 5. 2 to the 5th power is still a nice, pretty whole number. And so this is still going to be something we could easily do without a calculator. 2 to the power of 5. 2 to the power of 5 is 32. So the answer is 32,000 bacteria after 15 hours. Any questions? No? No? So I think a better question would have been to start to think about what happens at t values that are not pretty multiples of 3. Okay, but we can also solve things backwards. We can go in reverse. Part C asks us find t, find the time such that the output is equal to, what is it, 100,000, 10,000? 100,000. When will there be 100,000 bacteria? When will all this double, double, double enough for 100,000 bacteria to be there? Okay, so we have to solve this. We have 1,000, I'm sorry, not 1,000, 100,000. 100,000 must be the output when the input is our formula, 1,000 times 2 to the t over 3 power, solve for t. Good. So that's what we need to solve. Divide both sides by 1,000. These cancel. Base 10 number system means that in this case we can kind of cancel out the zeros and we end up with 100. Or you can get your calculator. 100 equals to 2 to the power of t over 3. It's in the exponent, so we know we have to use our log properties. So let's use our favorite log. I like ln. ln of 100 equals ln of 2 to the t over 3 power. That means I get to use that special property of logs to bring the exponent out in front like a linear factor. T over 3 times ln of 2 equals to ln of 100. That's just some number, right? Ln of 2 represents the decimal such that e to the power of that decimal equals to 2, but it's just some decimal. So I can divide this side by ln of 2, divide this side by ln of 2, and I end up with I need to make room here. I end up with ln of 2, ln of 100 divided by ln of 2 equals to t over 3. If I multiply both sides by 3, then we get to our final answer, that t equals to 3 times ln of 100 divided by ln of 2. Questions, 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 questions? Good, 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 good. Okay, so now we can get our calculator and approximate our results. So 3 times ln of 100, there's my numerator, 13.8155, and I want to take that answer and divide it by ln of 2, and I get to that result, 19.93, so on, so on, so on, so forth, 9316, let's say. Again, people don't really like having hours or a unit's time expressed as a decimal. So you could say 19.9316 hours, but given the educational system of our country, I think a lot of people would assume that this is 19 hours and 93 minutes, right? Because that's just, what does that mean, right? That doesn't work out. So this 0.93 is a percentage of the next hour, right? We're almost ready, almost really close to 20 hours. So you could round it to 20 hours, but we could put it in terms of minutes by multiplying 0.9316 times 60 minutes, right? Because it's a percentage of the next hour, and this is 60 minutes in 1 hour. Good. Okay, so if we multiply those two things together, 0.9316 times 60, you get 55.896. Okay, and at this point, you can just kind of round it to 56 minutes. Good. Okay, so our final answer would be that we will reach 100,000, right? The question was, how long will it take for the bacteria to reach 100,000? It will reach 100,000 in 19.9316 hours, or it will reach 100,000 in 19 hours and 56 minutes, approximately. Questions, questions, questions? Good, maybe, sort of. Okay, so the author did the same thing I did there for part A, for part B. Part C, same thing, 19.93, pretty close to 20 hours. Any questions? Good, good, good. Okay, so we expressed our bacterial growth in terms of doubling rate, right? How long did it take to double? That's a very useful way of describing something. But note that you describe you describe a unit a time in terms of doubling time. I'm just trying to. Let's go here. So we described a unit of time. We described how this population is growing by describing how long it takes for it to double, right? So we have used exponential functions with base 2 to model exponential growth. There's nothing special about base 2. We could also use base 3, for example. How long it takes for something to triple. We can express everything that way. Or we can express it in terms of a relative growth rate, where R is the rate at which it grows, sort of as a percentage rate. Good. Okay, so when we want to do that, this is our equation for it. So a population that experiences exponential growth increases according to the following model. N of t equals to n naught e to the rt, and that should look familiar, right? That looks like the formula for continuously compound interest rate, and they're the same thing. Whether money is growing by continuously compounding a rate r, or a population is growing exponentially, they're both the same formula. The same formula describes both situations. Good. Where n sub naught is the initial value, r is the relative growth rate, sort of as a percentage growth rate compounded continuously. Good. And t is time. Good. Okay, let's look at an example. Right, so this is very, very similar to the continuously compounded formula for interest. I think that's what this is pointing out. So let's look at an example. The initial bacterial count of a culture is 500. You start with 500. A biologist later makes a sample count of bacteria in the culture and finds that the relative growth is 40% per hour. Okay, so it's growing at a certain rate of described here at 40%. Usually in money, in terms of money, rates are usually given in terms of years. But here in this case, they're giving it to you as percent per hour. So n naught is, well, I'll put it over here. N naught is equal to, I have space down here actually. Okay. N naught is the initial amount, which was 500, and R is given as 40% per hour. So we're going to rewrite this as 0.4 or 0.40, either one, per hour. Part A says find the function that models the number of bacteria per t hours. So it's given in hours, it matches, so we don't have to do anything weird there. And remember the formula is this one, either the n naught r t, right? That's just this formula, n naught e to the rt. Good. And as long as these two things match, then everything should be easy. This is just going to be equal to the initial amount times e to the power of 0.40t. Right? That looks weird with that extra little thing there, so instead I'm going to parentheses around it. Okay, any questions? No. What is the estimated count after 10 hours? Okay, for part B, we're just going to use this formula and let t equal to 10 hours. Okay. What is the estimated count after 10 hours? All right, well, we just plug that into there. N of blank equals to 500 e to the 0.40 times blank. And that'll be 10 hours there, 10 hours there. And then we just get our calculator and work it all out. So n of 10 equals to, and then we get our calculator and type it all in. So this would be e to the power of 0.4 times 10. Well, that's an easy multiplication. It gives you that. And then you multiply that times 500, and you get that. 27,299, so pretty close to 27,300. Pretty close to 27,300. Any questions? Questions? No? So we start off with 500 in the culture growing at 40% per hour. 10 hours later, we'll have 27,300. Okay, after how many hours will the bacteria count reach 80,000? Part C, when will it reach 80,000? So this is what we want to solve, right? 80,000 is the output of that equation, where this equals to 500 times e to the 0.40 t. Good. Okay, so then we divide both sides by 500. 80,000 divided by 500 equals to e to the 0.40 t. Instead of dividing the whole thing and working my calculator, I'm just going to solve it the way it is for now and get all the way to t, and then I'll plug it all in that calculator. Right? Okay, so then I want to solve for t. I'm going to apply an ln function to both sides. ln of whatever this is, this division, divided by 500 equals to ln of this side, e to the 0.40 t. Right? These two operations are inverses of each other, so this just becomes 0.40 t equals this side, ln of this division of 80,000 divided by 500. And now we divide both sides by 0.4. So t equals to ln of 80,000 divided by 500 divided by 0.40. Good. So now we can punch that into our calculator and get our answer. Clear. We got ln of 80,000, 1, 2, 3, divided by 500 and all of that gets divided by 0.4. So I'm getting 1268.79. 1268.79. Hours. Right, so again, we can convert that into hours and minutes and get a slightly better answer than this. So if we multiply 0.6879 times 60 minutes, 12.6879 times 60 minutes, we get 41.274 minutes. So I can just round that to about 41 minutes. So I can say that it's going to reach 80,000 in 12.6879 hours, or 12 hours and approximately 41 minutes. Questions, 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 questions? So 10 hours to get to 27,000, and then just a couple more hours after that, 2 hours and 41 minutes past that, you jump from 27,000 all the way up to 80,000, right? Exponential growth. It's growing pretty quickly. Good. Questions, 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 questions? No? Mm-hmm. Okay, and then so the author did the same thing I did, and then we can use our calculator to graph this thing, right? Or Desmos. We've done a lot of that before, and we're running tight on time, so I'm going to skip that part there. And move on to radioactive decay. Before we move on to radioactive decay, actually I want to do something different here. Let's look at this just to highlight the differences between the two. So here we had bacteria initially had 500, and they're telling us that it's growing at a rate of, so it's a way of describing how fast it's growing, 40% per hour. We can also look for its doubling time. Remember, we have these two formulas, and they're both very, very similar. We had n of t equals to n naught times 2 to the t over a, where a is the doubling time. And then we have this other formula, n of t, which is equal to n naught e to the power of rt. So let's play around with these a little bit. This is n naught times, I can rewrite this a little bit and rewrite it as 2 to the power of 1 over a raised to the power of t. Good. Good. Okay, and so now these two formulas are the same. That must mean that 2 to the power of 1 over a is equal to e to the r. Good. Okay, so if we wanted to solve for a or to solve for r, we can do a little bit of some manipulation here. So let's apply ln to both sides. So ln of 2 to the 1 over a is equal to e to the ln e to the r. Ln of e to the r, which means that r is equal to this little equation, ln of 2 of 1 over a, right? So in other words, if you give me the value a, the doubling time, given the doubling time, I can figure out the growth rate. Good. Or the other way around. I can take this little formula here and solve for a by working out both of these things. Again, I want to do ln to both sides, but now instead of solving for this guy, we want to solve for this. So if we keep going, I get to move this exponent out in front. One of the properties of logs, so r also equals to 1 over a, ln of 2, and so multiply this side by a r equals ln of 2, and so a, the doubling time, equals ln of 2 divided by r. Okay, so in our little example here, they gave us the R value to be 0.4, so A equals ln of 2 divided by 0.4, which is equal to ln of 2 divided by 0.4, 1.7329. 1.7329. Okay, so it's not a very pretty nice whole number, but we're able to figure out how long it takes for this bacteria to double, right? Before we saw that it doubled every 3 hours or it doubled every 5 hours, a nice pretty round number. In this case, it doesn't turn out to be a nice pretty round number. It doubles every 1.7329 hours. So that's why it wasn't as convenient to use the doubling times to describe how this grows, right? So you can express how something is growing by describing its relative growth rate, or you can describe it by describing how long it takes to double. Good. Questions, 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 questions? Okay, all right, there's more on that coming up. Half-life. So when we think about a population growing, we think about, it's growing, and we think about how long it takes for it to double. How long does the population take to triple, quadruple, right? We normally think of it growing, but that's not always the case with populations. Sometimes they decrease, right? But normally, particularly in math, in math books, when they think of population, they normally think of it growing. Or it could be something like a virus growing, or a bacteria in a petri dish growing, or rabbits, population of rabbits, or just a variety of things, but they're usually growing. But then things also decay exponentially, and one of the most popular things that we think about is in the world of chemistry, where there's radioactive decay, right? So there are certain elements that are unstable in their natural sort of the natural chemical composition, and so they slowly break up into smaller elements, and it might happen in various stages, right? So we start off with some element, some really heavy element, and then it slowly breaks down into other elements, right? In 1 teaspoon of the item, there's billions of little atoms in there. Billions and trillions, right? We count them by moles. There's so many. We invented this way of counting how many there are. So there's moles in there, slowly, some of them are slowly breaking down into other elements. One of the most popular things that these radioactive elements, radioactive means that they're unstable. They're on their own. They're slowly breaking down. And as they break down, they release energy, and so that's the radioactive part of it, the releasing of energy. So as it's breaking down and releasing energy, that energy could be harmful to people if we don't take certain steps. We can use that energy to heat up water and turn it into electricity. Or we can accelerate the process and use that energy to make a bomb, right? So the difference between an atomic bomb and a nuclear power plant is just a matter of how slow or how fast this process is taking place. A very common element for it to end on is iron. So if we start off with 1 kilogram of a radioactive element, and sometime down the road, we leave it alone, and sometime down the road when we come back and we look at it, we're no longer going to have the same quantity we started out with. It naturally decays into other elements, like I said, often iron, but not always, and it breaks down slowly, and so you have less and less of the original radioactive element that you started out with. Sometimes the time it takes for it to decay is very, very quick, milliseconds. There are some elements that we've created in a laboratory setting that we have never really seen in the natural world, only in laboratory settings. And they can only exist in the laboratory setting for like a little fraction of time, seconds, and then they kind of break down into other things. But still, it counts. We created it, and so there's some elements high up on the periodic chart that only exist in labs before they break down into other items because they're unstable, right? Unstable elements. Any rate, so half-life. Half-life is a way of describing how long it takes for this this compound, this chemical compound, to decrease. And rather than using a percent decrease, right? It goes down by 1% every year, or it goes down by 17% every year. That could be useful if the numbers themselves are reasonable values. Like it goes down by 2% every year, we can handle that. But if it goes down by 0.00000000000000002%, man, I just lost track of all those zeros. It's really hard to keep track of that number if it's going down by a tiny little bit. So rather than using such small, tiny little decimals, it just makes more sense to think about a unit of time as a way of describing when we'll get to a certain milestone. And the halfway mark is a common milestone that we use. Okay, so in this example, radium-226, right? The 226 is it's part of the title, so don't let that confuse you. So radium-226 is presumably radioactive, so it will begin to decay, but it decays very slowly. It takes 1,600 years for it to decrease by a half. So if you start off with 100 grams of this sample and you leave it alone, you bury it in a cave somewhere, and you come back 1,600 years later, instead of 100 grams, you're going to have 50 grams. Okay? And then if you come back in another 1,600 years, you're only going to have 25 grams, right? Half of the previous values, and so on and so forth, so on and so forth, right? We just put these in a table format. I think they look a little bit better. So we have years over here. And then we have sample mass. So we start off at time 0 with 100 kilograms, and then 1,600 years later, it's a long time, that 100 grams, if we come back into the cave and see what's going on, now we only have 50 grams. What happened to the rest? Well, it naturally converted into other elements, right? There's a conservation of mass. They don't just disappear. It just changes into something else. So now when you come back 1,600 years later, you're not going to see 100 grams of radium-226. You're only going to see 50 grams of radium-226, and then the rest will either be other elements. Like I said, often iron turns out to be one of them, but there could be some copper in there, iron, gold, I don't know, different elements that it breaks down into. Some of it could be gases. Maybe it turned into some gases that have escaped. Maybe there's toxic gas in the air when you break open the cave and see what's going on in there. There might be some gas in the air. And then a lot of it is also released in terms of energy. So that might have escaped into the walls or out into the atmosphere. So that's what's going on with it. Then you leave it alone. You come back another 1,600 years later. So now it's been 3,200 years later. And instead of 50 grams, now we only have 25 grams. Another 1,600 years later. So now we're at 4,800 years. almost 5,000 years, and now we only have 12.5 grams, right? So it's still not so small that it's undetectable, and almost 5,000 years have gone by. So this grows pretty slowly. If I wanted to tell you the percentage decrease per year, I think you can imagine that that percentage would be tiny, small little percentage decay. So it would have a lot of zeros in it, and then it would be kind of hard to work with it, right? If I told you the percentage that disappears each year, it would be a tiny percent, right? Okay, so it's just more convenient to talk about the half-life rather than that tiny little decimal decrease, which is the percentage decrease per year. Okay, so half-lives are going to work like this. It's the same formula as the doubling time, except that, you know, for double time, we had n of t equals to n naught, and then it was 2 to the power of t over a, I think it was, right? So now this is half. The half-life formula is this one, but just put a half in there. It's m of t equals to n naught times 1/2 to the power of t over h. Okay, so before we used to say that a was the doubling time. Now h will be the halving time, how long it takes for it to half. Before we were doubling, so we put a giant 2 there because we were doubling it. And now we're halving, so we put a half there. Now if we do a little bit of algebra and rewrite 1/2, remember that this means that there's a little exponent of 1 here. And the way to simplify that, if we wanted to, is to rewrite this as n naught times 2 to the negative 1 power of this. And then that's how they get that formula. Oops, they use m naught, 2 to the power of negative t over h. Okay, but as you can see, they're basically the same formula. Good. Questions? And then if you wanted to go back to the standard expression of rate, decrease percentage per unit time, say how much it decreases each year, how much it decreases each hour, whatever, as a percentage decrease, then we go back to this formula, which is exactly the same as before. Good? Questions? Kind of, maybe, sort of. Okay, so now if we wanted to take this and relate it to our halving time, just like I did before, we can come up with a nice formula for it. So let's say that we wanted to figure out the half-life. So this is the formula that describes how it's going to decay when we have a rate given to us, right? A percent rate decay. And so if we set that equal to m naught over 2, which is half of the initial amount, right? That's your half-life. This is the initial amount. So if we take the initial amount and divide it by 2, this is half the initial amount. Half the initial amount. So if we can figure out how long it takes to do that, right? Find t. To do that, when we find t, we let t equal to h, which is the half time, the half-life. How long does it take to do that, right? So that's why they set this equal to h, since h is the notation we use to represent how long it takes for something to get half the initial amount. Good. So this is a way, what we're doing is we're finding a way to relate this rate, this relative growth rate, in terms of a time half-life. Good. Divide both sides by m naught, and we end up with 1/2 equals to e to the rt. I'm sorry, negative RH, where the H is T. Ln to both sides, we get this. Ln of 1/2 equals to negative RH. Divide both sides by H, and that gives you the R value. Or we can also solve for H. Good. Any questions about this? Yes? No? So the other way around is that H is equal to ln of 2 over R is one way. So if they give me the relative growth rate, I can do ln over R, and that gives me H, which is the half-life. Or this way around, where if they give me H, how long it takes for the element to have to half itself, the half-life, then ln 2 over H gives me the value R, where R is the rate of growth, right? How it's decaying over a unit of time, which is usually it could be years, months, days, depends on the substance. For decay, for this area of math, it's usually back to years. Any questions? Did I lose anybody? Okay, so all of that is wrapped up in this nice, convenient little package here. So radioactive decay models. If m0 is the initial mass of radioactive substance with half-life h, then the mass remaining at time t is modeled by this formula. Good. Where R equals to ln 2 over h, and that's the relative decay rate. Good. Okay, let's do an example. Polonium-210 has a half-life of 120 days. Suppose a sample of the substance has a mass of 300 milligrams. Find the function m of t equal to m0 2 to the negative t over h that models the mass remaining after t days. Right, so remember this little notation here is the half-life, right? Because 2 to the negative 1 power, right? So 1/2. I really wish the author would just write it as a half, but he's just noting that 1/2 is the same as 2 to the negative 1. So that's why there's 2 to the negative 1 times t over h. And so he wants you to find a model for this. So part A should be really easy. And then lots of other parts. Okay, let's do part A. Part A is going to have, well, the initial amount m0 is just 300. So that makes that part easy. And the half-life is 140 days. So really it's just a plug and chug situation. You just got to make sure that you keep t in terms of days. Right? So for part A, the answer is just going to be this formula. 300 times 2 to the power of negative t over 140. That negative looks weird there, so let me really punch it up. See there? So negative. Oops, sorry about that. Okay, we good? Questions for part A? Part B says, find a function of this form now that models the mass remaining after t days, right? So now, R is not given. They gave it to us in terms of how many days it takes for you to half-life it, but they didn't say what the growth rate was going to be. Okay, so we need to figure out R, and remember, R is equal to ln of 2 over h, right? It's given to us in this little formula. R is equal to ln of 2 over h. So for us, this would be ln of 2 divided by h, which was 140. Right, I'm solving part B here. Good. Questions? So R is equal to ln of 2 divided by 140. So I'm getting this 0.004951. I'll round it to there. Good. So now I have everything I need to use this formula to describe the way this is decaying. The formula m of t equals to m naught, which is 300, times e to the power of negative 0.004951. Whoa, 4951 t. Any questions, any questions, any questions? So both of these two equations should give me the same output for the same input. So if I let t equal to 3 and I plug it in here, that'll tell me how much of the original 300 milligrams of this substance should remain after 3 days. Plug a 3 in here, we'll get an answer. Plug a 3 in here, we'll get the exact same answer, right? This equation equals that equation. Two ways of describing the same thing. This one is describing it by letting me know that the half-life is 140 days. This one is describing it by letting me know that the relative growth rate is this 0.004951. It's decreasing at this percent. It's decreasing by, move this over, it's decreasing by 0.4951% per day. Right? It's a decrease. It's decreasing by 0.4951% per day. Good. Also, obviously, if I put in 140 here, it'd be an easy way to check. 140 times this decimal, and then e to that power times this. This whole thing should give me 150, right? Because we know that the half-life is 140. Any questions? Good. Okay, so for part C, find the mass remaining after 1 year. Okay, so be careful because everything so far has been given in terms of days, right? The half-life was given in terms of days. When we figured out the R value, we used days. So this is given in terms of days. So everything is in terms of days. So now they throw this little curveball at you after 1 year. So we're too smart for that. We're not going to fall for that. However, we get to use either formula, and this is a great place to check that they both give you the same answer. For part C, we have 1 year. T equals to 1 year, which is equal to 365 days. Okay, and we have our choice. We have two formulas we can work with, and it's dealer's choice. M of t equals to 300 times 2 to the power of negative t, negative 365 divided by 140. Oh, I meant to put a color in there. Oops, no. 365 and 365. And then that should give us the exact same answer as saying the other formula. M of blank equals to 300 times e to the negative 0.004951 times, and then putting in a 365 in here. Any questions? No? Good. Good. Questions? No. Okay, so let's grab our calculator and confirm that these guys are giving us what we think they should be giving us. So for the first one, we have 365 divided by 140 times negative 1. Oops, clear, didn't like that. Okay, I should have put a negative 1. Okay, let's just start over. 365 divided by 140. And then I want to take 2 and raise it to the power of that answer. So I can type in the negative 2.6071, or I can hit second and then ants right above the negative number here. And then that'll give me that previous answer. Enter. And then we multiply that by 300. And so I'm getting 49.237166, that guy. Okay, and that should give me a pretty similar answer to when I use this one. So let's make sure that they kind of give you about the same answer. So it should be e to the power of negative 0.12495 times 365. And multiply that by 300. And I'm getting something pretty close. It's a little off, of course, because of rounding issues, but they're fairly close. 49.23. Any questions? No? 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 Okay, so that was part C. Part D says, how long will it take for the sample to decay to a mass of 200 milligrams? And again, dealer's choice. We got two equations. Both of them solve the same thing. So we want to find T, right? T is the question mark, such that, find T such that our output is 200. Right, so we can figure out this. We got 200 equals to 300. Oh man, it's time to hiccup here. 300 times 2 to the power of negative t over 140. Solve for t, we got that one. Or, equivalently, we could solve this one. 200 equals to 300 e to the negative 0.004951 t. 4951 t. Okay, so both of them should hopefully be pretty easy. Either way, solve both of them at the same time. On this side, I would divide by 300. This side, divide by 300. I know that's going to simplify to 2/3. Same thing over here. 300 divided by 300. That will simplify to 2/3. So either way, that first step is the same. And I'll get that 2/3 equals to 2 to the power of negative t over 140. Or we get that 2/3 equals to e to the power of negative 0.004951 t. Okay. Either way, I'm going to apply my favorite log. It doesn't matter which log you apply. So let's do ln. It's my favorite log. So it'll be ln of 2/3 equals ln of 2 to the negative t over 140. I get to use our property of logs that the exponent goes out in front. That'll help me solve this. This will be negative t over 140 times ln of 2 equals ln of 2/3. Dividing both sides, or multiplying it by its reciprocal if you want to think about that instead. We end up with t equals to, its reciprocal is going to end up being 140 times ln of 2/3 divided by ln of 2, and there's this extra minus in there. Is that okay? what I did is I multiplied this side by 140 over ln of 2 negative, and that cancels out with everything, leaving out just the t. Whatever you do to one side, you must do to the other, so I also multiply this side by negative 140 divided by ln of 2. Good, 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 good. We're going to apply the same thing over here. This will be ln of 2/3 equals to ln of e to the negative 0.004951 t. And luckily here, these two are inverse operations, so that'll just leave me the negative 0.004951 t equals ln of 2/3. And if we divide both sides, we get that same answer right there. So ln of 2/3 divided by negative 0.004951 equals to t. Good. Either way, we get the same answer. Let's use our calculator and find the result. So here we end up with ln of 2/3, 2 divided by 3, close parentheses, enter, and then divide that by negative 0.004951. So we get that. T equals to 81, 89, 55. Okay, so then let's confirm we get the same answer over here. This would be ln of 2 divided by 3 divided by ln of 2. It gives you that, and then we multiply that answer by negative 140. And so we get the same decimal value, 81.89, rounding issues, of course, because of that, that percentage value over here, right? This guy was approximated, so it's not going to be exact, but pretty close, 81, 89, approximately. T is approximately 81.89. Good. And this is in terms of hours, right? Hours. It'll take approximately 81.89 hours in order for this substance to decay from 300 milligrams down to 200 milligrams. That was the answer to part D. Part D, how long will it take for the sample to decay down to 200 milligrams? Got that? And then draw a graph of these sample masses as a function of time. And again, we can type that into our calculator. Let's see what the author did. So for part A, we got the equation, the same equation we got. M of t equals to 300 times 2 to the power of negative t over 140. Remember, this is just a simple plug and chug into our formula for half-lives. Right? Then we can use this little formula to find the relative growth rate. Well, in this case, relative growth decay. So this is like, it's decaying at a percentage of minus 0.495%. Gets you the same formula we got. Converting it into a year into days, we get the same answer there. And yep, 81.9. So get that, and then we can just type that into a calculator and get our answer, our graph. And then we can use that trick we used before to find more complicated results. Or it gives you, not necessarily more complicated results, but it gives you another way of solving things, right? So let's find this graph in our calculator real quick. We've got a couple minutes. So let's go to y equals, and let's type in our equation. And you could do either one. Again, you should get the exact same graph, right? Because they're the exact same equation. Same inputs give you the same outputs, so it should describe the same graph. Okay, so this should be 300 times, and then e to the power of negative. Make sure you use this as the negative and not this one, because that's subtraction, and it'll give you an error sign. 0.1249551, and then the input variable, which we have to go back to x. So there it is. And let's go to our window to get something very similar to this. Let's go from the x minimum, let's go from 50 to 200. Let's make it 300. And then the little tick mark things here, let's make it in multiples of 50, so it kind of matches the graph there. And then the y's goes up to, let's make it negative 100 up to positive 500. And the little tick mark things, we want to put them at every 50. That's fine too. Let's see what our graph looks like. Okay, similar to that. Not as pretty, but similar. And now that we have this graph, remember that we can use this as a way of solving things. Because if we have m of t equals to 300 e to the negative 0.004951 t, and I wanted to say, when does m of t equal 200, right? When do we get down to 200? We're trying to solve this. 200 equals to 300 e to the negative 0.004951 t. Okay, so on our graph, we're trying to find when this function reaches, right? It's getting smaller and smaller and smaller. We're trying to figure out when it reaches right there, right? When it reaches 200. So in our graphing calculator, we can just graph this line. Y equals 200. Right? We let this be y sub 2 equals 200. We already have this as y sub 1. And when we graph them, we look for the intersect and the x coordinate, in this case t, the t coordinate of our ordered pair where they intersect will be our answer. Good, let's do that real quick. Back over here, let's go back to y equals. I want to set when this equals to 200. Graph, there it is. I want to find that intersection right there. So second, calculate intersection is the fifth option down. Hit enter once to select the blue one, hit enter twice to select the red one. Oops, I accidentally hit clear. Graph. Okay, sorry, doing it one more time. Second, calculate intersection is the fifth option down. Hit enter once to select the blue one, hit enter twice to select the red one. And now you want to use the little arrows to get pretty close to where the intersection is. Right around there, right? It says guess. Then hit enter. And there's our intersection, and there's our answer. The coordinate is 81, 89. Right? So that means that this little ordered pair right here is the ordered pair 81, 89. 81.89, comma, 200. Good. So this is our answer. T equals to this. T equals to 81, 89 will be the input value of t such that the output is 200. So that was another way of solving that question. Any questions at all? Questions? No. Okay, the only other concept in this section is Newton's law of cooling, and like I said, I didn't assign any questions with Newton's law of cooling, so we don't have to worry about it. And there aren't any, it's not going to be represented on our next test. So this is the end of the material on the next test. We'll stop here. It'll be a week from today, same format as last time. Next Wednesday, class ends, the test becomes available. You can take it at home on your own. Make sure you show all your work, and then you're gonna upload it to the Canvas account. So it'll be another one of those little Dropbox things on. Well, there'll be another place for you to upload it onto Canvas. Good. Any questions? Okay, then have a great day. I'll see you tomorrow.